Hello, my name is Anthony Bocan, and in this video, I will introduce to you some of the main features of the ANAX Hyperion software, an intelligent lens design software. In optical design, the conventional approach consists in considering the input of light to the system and the desired output of light. An experienced optical designer will need to take into account this input and this output to produce a guess initial optical layout that he will manually enter into the system. Through simulation by ray tracing of the system, the output light can be predicted, and when compared with the desired output of light, the designer will try to insert lenses or optimize the parameter of his initial guess and repeat until the two match. It is well known that this task is quite demanding and requires a lot of knowledge, such that usually only experienced optical designers are able to carry it out successfully. ANAX is proposing a new approach in which the software can act automatically based on just the knowledge of the input of light and the desired output of light. To achieve this, our software leverages AI-based laying out of initial guesses and a special inverse ray tracing algorithm through which freeform surfaces can be automatically constructed. The main modules of Hyperion are listed here. First is the basic module, which contains basic functionality for numerical optimization of lenses and inverse ray tracing to build freeform surfaces. On top of it, an AI module can be added, which is capable of providing very good initial guesses based on the most basic of specifications, such as the focal length, entrance pupil diameter, and field of view of the optical system. Finally, a microlenser module is also available, through which a very complex arrangement of arrays can be produced, and each array, each lens on the array, can be defined as an individual freeform lens. So first I will introduce the features of the basic version of Hyperion. One of the main advantages of the Hyperion software is the simplicity of the interface. There are very few buttons, which all represent automated tasks, such as the layout by AI, geometry optimization, and automatic construction of freeform surfaces. The optical components are listed in one main table, and instead of the usual Surface 1, Surface 2 approach used in most conventional optical design software, Hyperion has taken the approach of calling a lens, a doublet, and so on. This makes for a linear approach and makes identification of the optical component possible very easily on the layout shown in the bottom. It's also noteworthy that by using this optical component approach, when pulling out optical element from the catalog, we maintain a link to the product on the supplier website. So it's very easy to make a quick check and, if needed, place an order for catalog products. The basic version of Hyperion features an automatic freeform surface design algorithm. This freeform surface design algorithm is simply using Fermat's principle, which says that light always takes the fastest path from one point to another. This is something that most people who have studied basic physics at high school will remember. Starting from a point A going to a point B, light will travel in the fastest path when taking into account the different speed of propagation through the different medium. This can be explained very easily through this animation here showing the propagation of wavefront, and the change in curvature that occurs when the speed of propagation is slowed down by the more dense optical medium. Here I will briefly explain how the automated construction of freeform surfaces in Hyperion takes place. Remember, there is only one design rule: minimize the optical path length. Here we have an object point and an image point, which is our target. In between, we start with a guess as an optical blank, just a glass window. First, send a ray to the blank and intersect the first surface. Next, we find that there are many possible paths going through the glass and then the medium behind. But by applying Fermat's principle, we know that the shortest path should be elected. Keeping this path, we can now consider the condition of refraction at this interface, Snell's law, which itself is a consequence of Fermat's principle. It is possible to calculate what should be the plane of incidence that will produce the right combination of angle on the incident and refracted side. Using this tangential plane, we then send the next ray. We apply again Fermat's principle to find the shortest path, define a new tangential plane for the incident ray, and then go to the next ray, and so on. I think it's possible to see here how this progressive approach progressively constructs a freeform surface made of points and normals. After completing the ray tracing, the algorithm will attempt to fit a polynomial surface to this collection of points and normals. The next step will then be to reiterate the same procedure, but instead of starting from a blank, we will start from an actual polynomial surface. To illustrate the power of this algorithm, I will show a very simple example here. We have a simple catalog lens, which is just a convex-convex lens, a spherical product. We have an object on the left side, and on the right side you can see the associated spots in the imaging plane. Of course, because this is a simple lens, and we are very far from the paraxial case, the image ends up being extensively blurred due to a variation of aberrations. By using the construct algorithm, we can simply specify the position of the object plane and that of the image plane, and the algorithm will automatically calculate a polynomial surface that can provide the best imaging across the entire aperture of the lens. You can see here a simulation of the resulting image, which is much sharper than the initial image obtained through the spherical lens. The basic version of Hyperion contains a variety of analysis tools, including ray tracing in 3D, ability to generate photo simulation by interpolating the point spread function, generation of spot diagrams, distortion diagrams, and aberration coefficients. The software also features regularly updated catalogs of commercially available lenses from suppliers such as Sorlabs and Mondoptics, and conveniently produces up-to-date estimates on the price of each optic when searching, for example, by focal length, diameter, or type of lens. A catalog of material is also available containing some of the most widely available materials from suppliers such as Schott, Ohara, and so on. The basic version also contains a number of import and export facilities. Mainly, it is possible to import and export design for exchange with software such as Zemax, Oslo, Code5. The designs, specifically freeform designs, can be exported to CAD files, and CNC file for micromilling and diamond turning can also be generated directly from the application. A small window is shown here showing the level of details that can be achieved when generating such CNC files. Next, I will give an overview of the Hyperion AI module. When designing multi-lens systems, the optical designer usually refers to charts that help classify the types of optical system as a function of field of view, numerical aperture, and also perhaps the focal length of the system. Based on this initial survey, it is possible to then check either examples from ray tracing software or go through a pattern search to look at prior art designs. After making a choice of this initial guess, the designer will then lay out some group of lenses which are known to reduce certain types of aberration. He will then rescale the system to achieve the needed focal length, and then simulating the spots, inserting more elements, optimizing some surfaces, he will iterate. It is noteworthy that these tasks are rather well suited for machine learning. The Hyperion AI Assistant module was trained on more than 10,000 historical pattern designs. This initial supervised training was then complemented with extensive unsupervised training, where the neural network was coupled with an optical ray tracing algorithm that allowed it to find a good combination when interpolating between these historical patterns. We therefore propose a simple interface where, from a few input parameters, the field of view, the diameter of entrance aperture, and the effective focal length, a number of propositions, suggestions are provided by the software in increasing complexity. In each case, a report is provided of the spot RMS, as well as some of the most basic aberration coefficients. Based on this information, it is possible to set yourself a target for your spot size RMS, and at the same time consider the cost associated by the increasing complexity of the system. Next, I will introduce the microlens array and micromirror array module of Hyperion. Anyways, let's consider some of the advantages of microlens and micromirror arrays. A conventional lens is designed to have a single focal length. This means that when placing a screen at a known distance from the lens, it is only possible to get a clearly focused object point for a given distance in front of the lens. If the point is further out or further in, it is not possible to obtain a clear focus on the screen. By replacing the lens with a microlens array made of several segments, it is now possible to adjust the curvature of each segment in order to capture light from different distances to the lens. In this case, each point will form a sharp spot on the screen. There is, however, one small issue. Considering the distance of the point to the lens, the solid angle of light that is collected will vary as a function of this distance. For a point very far away, the solid angle omega-1 will be significantly smaller than the solid angle omega-3 obtained for a nearer point. The issue of this unequal collection of light from different distances can actually be resolved by adjusting the surface area of the various segments on the surface of the lens array. In the example shown here, the very far away point has been allocated a much larger surface area than a nearer point. As a result, the solid angle of light can be equalized for all distances measured by this device. Recognizing the need for flexibility in designing layouts of optical segments, the Hyperion microlens array and micromirror array module provides the user with a variety of segment layouts from hexagonal to annular and rectangular, as well as the ability to freely allocate surface area for the various segments comprising those lens arrays. An optimal topology version is also available, in which, starting from a given pattern, the pattern will be automatically topologically optimized in order to fill the available aperture of the optical surface. At this point, the input and output of each lens can be specified in a manner reminiscent of the example I provided in the basic version. Using our automatic freeform surface construction algorithm, the software can then use this input-output combination, whether it's a field angle, an object point, or an image point, to then construct the individual freeform surfaces of every one segment on the surface. The Hyperion microlens array micromirror array module opens the door to many new types of application in optics and photonics. As a simple example, I will show here how a microlens array can be designed that has a capability to achieve with a single lens a performance very close to a multiple lens achromatic system. The concept is simple. Divide the surface into segments that are allocated a single wavelength. Then, design and construct the surface for that single wavelength in order to obtain diffraction-limited performance when generating an image on the image plane. The selection of wavelengths would be coupled here with the use of filters in front of the microlens array. Ray tracing simulation of the spots shows that this microlens array design can achieve excellent achromatic performance for the entire field of view of the design system. This compares very favorably against other types of achromatic systems, such as the doublet lens shown here above. Using the CAD export facility and NC file generation facility of the Hyperion software, the actual MLA can be produced very conveniently. Here we show comparison of actual photographs taken through a variety of lenses, including a diffraction-limited A-sphere, a doublet commercially available, and the designed microlens array for achromatic imaging. This information was published in Optica in 2022, and you are welcome to refer to this article to get an idea of the capabilities of this new type of freeform microlens array. Another innovation of the Hyperion software is the use of topological microlens arrays. Here, an illumination pattern is imported from a vectographic file. This target illumination pattern is then topologically optimized to fill the available optical aperture on the lens array. This step allows a more efficient collection of light from a single point source or from a collimated source of light. Next, using the construction algorithm, the freeform surface of each segment can be automatically computed, and the software can, after the light has passed through this topological optimized segment shape, produce the original pattern of illumination on a screen. One more advantage of this approach is that the collection of light assigned to one area, for example here area 4, can be increased by a factor of 1.25 or 1.5. By doing this, the software will automatically allocate extra surface area, which will result in a more intense pattern of light resulting on the screen. This video shows the actual implementation of this concept to produce an animated version of the ANAX logo. Here we have 3 topologically optimized apertures, behind which 3 point-like sources of light have been placed. This was produced using acrylic, and the step file and CNC file needed for rough and fine cutting were all generated with the Hyperion application. There are a number of applications for this topological optimization of illumination pattern. Here we can mention projection headlight for cars and coupling also of light with fluidics in microfluidic system. Thank you for following this introduction video of the Hyperion software all the way to the end. And if you have any question or would like to obtain a demo license key available for 1 month, please feel free to contact us at bocan@anax.jp.